Hey guys, it's Mr. Wynn, and I want to talk about geometric sequence. This is the first section of Unit 5, kind of an intro, but it's going to be about geometric sequences and how it relates to the actual exponential functions we're going to talk about this unit. So for the essential question, I want you to write, how do I write functions from geometric sequences? Geometric sequences. All right. First thing I want to talk about is the actual form of an exponential function. Okay. You always have a parentheses b raised to the x. X is an exponent. Okay. That's why it's called an exponential function. So this is called an exponential function. Exponential function. All right. Notice how the x here is always the exponent. It's kind of raised. It's like a little tiny x, but raised to the x. All right. But the a and b will always be numbers. Okay. A and b will always be numbers. So a is what's called your initial value. Initial value. It's what you start with. Okay. B is called your rate. How is it changing? Okay. And then all of that's raised to the x. So you may see something along the lines of like 2, 5 to the x, or 4, 10 to the x, right? Those are usually how those equations look like, okay? Those are just examples. That's how it looks like, okay? But how we actually get those numbers, I'm going to erase that. If I give you an example, here's a pattern, right? 2, 6, 18, 5, 162. Your first value is always the initial value. So if I write it in that form of a to the b to the x, right? Your a will always be 2. Now we just got to figure out what b is going to be and raise it to the x. To find b, okay, you always take the second number, right? We're going to find b. We're going to take that second number, 6, divided by, okay, the number before that. So in this case, it will be the 2, okay? 6 divided by 2 will be equal to 3. B would be 3, okay, to the x, okay? Notice how it works for any of them. If I take these two numbers, right, I'm going to take 18 and 6. 18 divided by 6 is also 3, right? If you take 15 and 54 and 18, all of those have a constant change of being multiplied by 3. Because if you notice, 2 times 3 is 6. 6 times 3 is 18. 18 times 3 is 54. You're changing geometrically. It's being multiplied, you know, as we go on, right? So your graph is going to like go up quick, right? We're used to things going up where, you know, steadily plus 3, plus 3, plus 3. These are going to go super fast, right? They're going to go up like that, okay? Just to give you a preview of how the graphs look. But let's look at example 2. So again, your initial value is 12, right? So we know 12 goes in front. And then figure out how much is it multiplying each time. Easy way to do that. Take the second number divided by the first. So 6 divided by 12. That actually reduces down to 1/2. We'll put 1/2 where that goes. Okay, simple enough. Now watch this. You got a couple negatives, right? This looks a little bit different, but the same rules apply. First number is 12. All right, take the second divided by the first, negative 10 divided by 5 equals negative 2. That's going to go where the b is. Raise it to the x, just like that, okay? Even if those negatives you see there, you're still just going to have a negative b. Notice that? Okay, so it can be negative, all right? Now here, even fractions. It really doesn't matter what the number looks like, okay? Don't be scared off by fractions. You still start with your first number, so 15 over 2, that's okay, we can leave that. And then find out your b by taking the 5, dividing it by 15 over 2, so 5 divided by 15 over 2, and you could go with the calculator, do whatever, but that ends up being 2/3. 2/3 would go in here. Okay, let's go to the calculator, just put that in. 5 divided by 15 over 2. 15 over 2 is actually 7.5. So if you wanted to see how I did it, 7.5, which is the same as 10 over 15, which then reduces down to 2/3. Okay, this is kind of how I did it in my head, but just know that you can put that in the calculator and use it. Okay. All right. What if I give you something like this? This is what's called the recursive rule. See how it's written a little weird? But you're given the same information, okay? It says to write the exponential equation of the sequence, okay? If I give you something weird like that, okay, there are only a couple things that are important. Your A1, that little one there, actually means the first number in that pattern. So if you have a pattern, you start with 12. This 2, notice how it's being multiplied? 2 times that an minus 1, whatever, right? That 2 tells you what the rate is. You're multiplying by 12, just raise it to the x. You've got your equation, okay? But if I ask you to write out the whole problem, right? It'd be like 12, and then 12 times 2, 24, 24 times 2, 48, right? You're multiplying by that 2 right there, okay? And then you'll have that pattern just like above, okay? Here's another example. If A1 is 5, that means you start with 5, and then it says to multiply by 3 here. It's kind of in the middle. Notice how 3 is kind of in the middle there. That's your exponential function, okay? Now, what if I ask you for a certain term? Well, go ahead and write the equation out. So A1 is 10, right? So I'm going to start with 10. And then I'm going to take the rate of 3 to the x, right? But what that essentially means is you start with 10, and then you're multiplying by 3 every time when you continue that pattern. So 10 times 3 is 30. Times 3 is, right, is going to be 90. Times 3, 270. Times 3, it's going to be 0, 1, carry the 2, 6, 8, 10. And then what is the fifth term? We could stop there, right? Here's number 1, number 2, number 3, number 4, number 5. 810 is the fifth number in that sequence. 810 would be the number you're looking for there. All right? And that's basically it, right? It's a nice introduction to geometric sequences, which leads to exponential functions. And yeah, thanks.